Okay. Hello everyone, my name is Zed Mansour. I'm a biotechnology graduate from MSc University, and today we will talk about the mass spectrometry theory and application, which is part of our course of this semester, which is instrumentation in biotechnology laboratory. This will be a mini introduction, so we will not get into too much detail. By the end of this video, you will be able to understand how earlier mass spectrometers worked and have a better intuition of quadrupole mass analyzers. Okay, so what is a mass spectrometer anyway, right? A mass spectrometer is an instrument that is able to differentiate mass over charge ratio of multiple ions from a sample that's been vaporized into a gas state, and it's able to quantitate each mass over charge ratio of each ion in this given sample. So a general mass spectrometer has this compartment. It has an inlet for the sample. It has a source to get this sample to be ionized, and then the ions get sorted by a mass analyzer, which can be a quadrupole or a magnetic sector or time of flight magnetic analyzer. Sorry, mass analyzer. And then they have the final ion detector, which basically just gives you a, an electrical current whenever an ion hits this detector. And then you gather this data and you have your normal mass spectrum here. This is pentane here, I think, yes, pentane. That's been defragmented. This is the mass of the larger molecule. This one is these parts over here that's been diffracted, and so on. So the mass spectrometer generally can be seen as a detector for the samples that's being fed to them. Samples can be in either gas or liquid state. The liquid, it turns into a gas in the mass spectrometer. So whatever your sample is, it needs to be in a gas form. Okay, so if it's in a gas state, that's fine. If it's liquid, then you need to turn it into a gas. If it's solid, you need to preheat it to get some ions or some gases to escape from it to reach the ion analyzer. Okay. The sample can also be pre-separated using a chromatography column, which can be a very powerful tool for analytical chemistry, analytical biology. So why should we care, right? Well, a mass spectrometer has a plethora of application in our biology field. You can use it to detect or quantitate any metabolome, the metabolome of the patient in the serum or the proteome, or even their genome. You can even, if you know how to work with the mass spectrometer, it needs to be very, you need to have certain experience, but you can do that as well. You can also detect isotope of certain drugs if you want to. You can detect specific drug concentration in each period of time to get the pharmacokinetics of a drug in a human plasma. There's a whole lot you can do about it. So it's a very important tool. It's a very powerful tool that everyone should learn about. Okay, so what are the types of mass spectrometers? Okay, so as we have seen, there are the major type of mass spectrometers is the magnetic sector, the quadrupoles, the ion trap, the time of flight, which are seen right here. There's a magnetic sector. These are quadrupole, like these are quadrupole, and this is the magnetic sector. We will focus on these three, and unfortunately, as I mean, it's a very powerful tool, but we will have to neglect time of flight for today. Also, it's a very powerful for proteomics. We need it, and a type of ionization for solid sample. It's very powerful. We really need it, but right now we just focus on this for preliminary introduction. So the magnetic sector, let's start with that. Okay, so the magnetic sector, this is a normal magnetic sector that one would be able to see in the laboratory. It can be seen in gas in GCMS, the older version, of course. It has a gas inlet for samples, and then a heating element and electron beam to ionize it. An ion hits the molecule and gives the one electron escapes from it, so it turns into a cation. So the cation here, it's accelerated under a potential field, and then the acceleration path gets deflected using a magnet. Each of these deflection paths is a semicircle. You can see it as like a semicircle here. It's part of a circle with a radius r. This radius is very specific to each mass over charge. So if you know uh, each of these components, the voltage and the magnet, you can tell what is the mass over charge ratio for a particular ion that hit the detector. Remember, the detector has no idea what is the mass over charge. It only gives you an output if an ion or an electron hits it. So it has no idea what's going on. It just gives you a peak whenever a certain ion or electron hits it. Okay, so that's what we were talking about. So we control the magnetic field strength and the voltage. So that means we can also look at here. The radius here is actually fixed. So we bend the instrument so that it allows only one radius to be entered. And this allows us to manipulate the magnetic field and the electric field, which only allows like a single mass or over charge ratio to be passed. And this helps us in detecting different mass over charge ratio. Okay, why is it important? What can we do with it? Well, the magnetic sector or generally mass spectrometer can be used to find the empirical formula of any certain of a compound that you're dealing with, and and if it has a higher resolution, it can give you the isotopes, which is also very important if you want to find the empirical formula for your molecule. Ionization with electron bombardment was also possible to be predicted using different rearrangement methods such as McLafferty rearrangement or Diels-Alder rearrangement or other methods that allows us to create like a virtual library for potential molecule diffraction pattern, and we can compare that to an experimental data, and from that we can create a plethora of libraries that we can then use to detect unknown samples or unknown matrices from a biological sample and so on, which is a very huge deal. The rearrangement here, it's actually a very deep subject that we will not be getting into, but you should know about it. There is different way to predict diffraction. This one is the McLafferty rearrangement. Oops. So electron bombardment here, it knocks off an electron. This oxygen takes up this hydrogen. Then this one is neutral, and you get left with this cation here that enters the mass spectrometer. This is McLafferty rearrangement for carbonyl carbons, carbonyl compounds. Retro Diels-Alder is for cyclic compounds and so on. But you should know about that mass spectrometers will not help you to differentiate isomers, but it can help you differentiate isotopes. So this is very important. Mass spectrometers for isotopes, but not isomers. If you want to detect isomers, then use proton NMR. Okay, why does it even work? Is it magic? Like how in the world can I do that, right? So let's break down each component of the mass spectrometer here. So we have the kinetic energy here from the acceleration of the ion. Okay, so this is our these are plates. Okay, and you have the ion going through a slit here and accelerated. So it has a potential energy equals to the voltage here and the charge. So when it travels from A to B, it transfers this potential energy into kinetic energy due to conservation of energy, right? So here we have it. The potential energy when it's resting here under the voltage, it's equal to the charge over the voltage. And when it's let go, it turns into a kinetic energy, which is the usual half mv, which is the velocity. And due to conservation of energy, the kinetic energy will equal to the potential energy, which leaves us with this nice equation. So let's look at the force, which is the other type of the other chamber here. It's the magnet, which is which causes the ion to have a magnetic field induced force, which is called the Lorentz force. The Lorentz force here is equal to the charge times the field strength times the velocity times sine theta. Sine theta is the velocity vector and the angle with it with the magnetic field. So this is the theta here. And when it's perpendicular to the magnetic field, it equals to 1. So when it's 90 degrees, sine 90 is equal to 1. So this one cancels out, and the ion experiences a circular motion. So circular motion, what does that cause? It causes centripetal force. Remember centripetal force? There is a difference between centripetal and centrifugal. Centrifugal is away from the circle, and centripetal is within. So centripetal force is equal to this, and we can just make them both equal to each other because the ion experience force due to magnet, and it's also centripetal force, so they are equal to each other roughly. And we can take that. Okay, so the magnetic field force and the centripetal force we can equal to each other, and then we get the velocity here. And okay, this is the charge, and then we know that the kinetic energy is equal to this from the previous slide. We can get, look at this, it has a velocity and this one also a velocity. So we can put them all together, and then some algebra, we get this nice equation. Which, look at this, you can tell the mass over charge ratio knowing of the field, the strength of the field, and the voltage between the two plates that causes the ion to accelerate. And the radius here, well, I don't know the radius of the trajectory, but we can make our instrument has a fixed radius so that this one is fixed, and we can manipulate the strength here of the magnetic field and the voltage. That tells us when B is equal to X and V is equal to Y, we get is exactly M over Q, which will be assigned to this. You can look at it as a histogram, like here it's like Benson here, and this one when this equation uh, when these parameters are met يعني. I mean, so the detector it has no idea what are mass over charge. It gives you the amount of ions that hit it at a particular time when B is equal to X and V is equal to V. So that means that M over Q is in this bin over here over this diagram or histogram, of whatever you want to call it. So what is I realize that our time here has been exceeded, but you can cut it right here if you want. But I will just continue if you wish to. So let's talk about the quadrupole. A quadrupole is also a powerful tool. It's not as high resolution as the magnetic sector, but has a very high scanning rate. Because remember, look at this. The magnetic sector, it needs time to change the magnetic field, and it needs time to change the electric field together. So this causes the scanning time to be longer. So each sample, each mass over charge, it takes longer time to be analyzed for a large group of samples or for large analytes within a single sample. So you maybe have a single sample and you need to analyze a lot of things inside it. Each of these things will take a very long time because the scanning rate is very slow when it comes to the magnetic sector, as well as that you need higher maintenance, that needs a higher vacuum. It's very intense when it comes to operation. But for quadrupole, look at this. Four rods. Exactly, like can you even imagine that? You can do the same function as a magnetic sector with these four rods right here. These four rods, these are the positive rods. You have a positive charge being supplied to it using a like it's being supplied a positive charge, and these two poles here, they are it's supplied negative charge that is equal to like the negative of the positive. So it's the same amount, but in the opposite direction. So you can filter different mass over charge using only voltage. You don't need magnets anymore. So how does this work? So you supply it an alternating field, alternating current. And this current causes an alternating potential field. This potential field has a positive and a negative. So when you add a positive ion right here, the ion gets jiggled around within the quadrupole. It's like if it's very light, if the ion is very light, the ion will be deflected out. If it's very heavy, it will also be deflected out. But if you have it just the right amount of jiggling of the alternating between the positive and negative current, you will get single mass over charge to pass. So if this one is either too heavy or too light, it will be deflected. So we have now essentially we have created a mass filter, and you can look at it this way. So look, it has a direct current right here being supplied to it and an alternating current supplied to it. This is the positive anode, positive cathode, and this is the anode. So this causes an alternating potential field. So this is the X for the X rod, which is equal to the voltage. These are the voltage being supplied to the X rod. The voltage of the direct current plus the voltage of the alternating current. And we have it like here. Look at this. It's alternating. So remember, you have the ion going through. It's being jiggled around by the different potential fields. And you have the Y rods. It's the negative rods right here. And it's equal to the negative of the positive rod. So it will be like that. Okay. So VDC equals plus VRF. RF is radio frequency because you know it's alternating in the radio range. And this is the this sign here is the radio excuse me, the frequency, and this is the time. Okay, so essentially you have the ion here, gets bounced around. If it's right, if it's not right, if it's too heavy or too light, it gets deflected out. We don't need it. So what can we do with this? This is very, very powerful. You can add multiple quadrupoles to detect multiple things. You can even detect you can even do a scanning mode with your quadrupole where you detect the smallest or the lightest ion, and let it pass through the detector, then the next lightest ion, then let it pass to the detector, and so on and so on. So we get a scanning mode using this method, or you can let only a single one in. So this is very powerful. You can use it in a plethora of ways. So here is an example of a triple quadrupole tandem mass spectrometry. So here you have the inlet sample. Which remember, you can either have it as a liquid or gas phase, but the liquid needs to turn into a gas phase because you cannot enter anything into a mass spectrometer, the mass analyzer. You can't enter anything except gas because it deals in in ion gases. Like the gases are ionized, and it only plays around with this gases state. So here you have the inlet sample. It goes through, it can be coming from an HPLC or UPLC unit, which is already pre-separated. It goes through here. It gets charged. Look at it. It's called the nebulizer. It's like the perfume head, you know. It psst, exactly like that. It gets a charge, then enters as a gas. So the quadrupole here, it lets only one thing out, and leaves all the other. And the second quadrupole, this is also a quadrupole in the middle, but it has been compressed with inert gas, so it causes diffraction. But remember, the last biomagnetic sector, it uses electron bombardment to cause a diffraction. This one, it causes diffraction using collision-induced diffraction, which is called CID, collision-induced diffraction. Okay, so it diffracts here. It only lets a single daughter ion to pass through, and the rest is expelled. So this is also very powerful. But if this is the parent ion coming through the first quadrupole, it lets in. Everyone else is expelled. Then it diffracts into two daughter ions. One of them is left, and we only detect a single daughter ion. This goes to the detector, and this is right here. Okay, so what is this called? The one I just talked about was called an MRM or MSMS operation, where you only let a single parent go through. You've defragmented using collision-induced diffraction. Then you only pick a single daughter ion, which only passes to the detector. And knowing the voltage here and there, you can give out the mass overcharge of whatever gave the signal. So your instrument constantly measures the voltage, the radio, the frequency of alternating current, the direct potential, and so on. So knowing all of these gives you the mass overcharge. The detector here only gives you intensity. Be aware of this, okay? Then you have the scanning mode. Scanning mode here, it doesn't use any of these. It uses them as an ion duct, like a lens. So it doesn't cause it to fly off or anything. It allows all the ions to pass through, and the diffraction, the collision energy, the collision chamber here, excuse me, it's not even turned on. It also works as an ion duct, so it allows all the ions to pass through. Then here you have the scanning mode where you let a single ion through, then the one heavier than it, then the one heavier than that, then the one heavier than that, and the detector here it gives you the intensity for each mass overcharge, which is also very powerful. So here are the different operation mode for a usual quadrupole. You have the MS operation and the MS mode. We will focus on the MS. The MS mode is very mundane. We have seen multiple things that look like it, but here we have it. The first operation mode that we will talk about is called the precursor ion scan. The precursor ion scan, the first quadrupole here is in scanning mode or RF mode. Excuse me, the scanning mode here. Okay, so the scanning mode, it lets a single ion through, it gets defragmented, then you allow a single ion in that you know about. So if this is the right precursor ion, it gives you a high intensity for the one that you're looking for. If this one is the right one that you're looking for, it will give you the precursor that you're looking for right here. So this one gives you all the precursor ions that gives you the highest intensity for whatever you are looking for. Then you have the second one is called the product ion, the product or daughter ion mode, which you pick a single parent, you defragment it using collision energy, then you do a scanning of all the daughter ions that coming from it. So if and using this, you can get all the fragment ions that are possible to be brought from a single product ion or single, excuse me, single parent ion. Then you have your normal MRM, which you pick a certain parent, you fragment it, then you pick a certain daughter. This is also very powerful, and we use it to quantitate drugs or quantitate something that we were trying to. Um, no, you're trying to quantitate something in a biological matrix. This is what we are using this for. Then you have the product ion conformation scar or PICS. It's the same as MRM, but you add at the highest intensity or after the highest peak of your detection, the last quadrupole start going through a scanning mode. But why do we do this? It does this because it's a confirmation mode. It gives you, okay, so this one is supposed to be mass overcharge of X, and it gives up a daughter of Y mass overcharge. But to confirm it, here are all the possible fragment ion that comes from this parent. So we will look at it and like, oh, okay, this one is the right fragment. So we are doing things okay. Then you have other types of fragmentation or modes of operation like the neutral loss. Neutral loss here it's used more mainly for lipid detection, and it basically it has how the way it works is this mass here. It does the scanning. Both of these do scanning modes, and the difference between them is the one that gives up the peak. So this is also very interesting because you right here in neutral scan we don't detect any cations, we detect the loss, the things that did not enter our mass spectrometers, the things that should have got in but did not, the neutral ions. Okay, this is the typical modes of operation for a quadrupole. Look at this. This is MRM of 20 mass pair. 20 mass pair. Like, remember, there are three quadrupole. One is set on the first quadrupole, then the third one is set on the daughter. So these are 20 molecules that we are trying to detect, and he detects it from a period from 0 to 3 minutes. Then afterwards, he switches to 14 other molecules. And look at this. This is called ionization mode, positive ionization mode. Positive ionization mode means he only lets in positive ions through the mass spectrometer. There is also other types of ionization like negative mood or so on, or electrochemical ionization. Uh, okay, so this is also, I look at this ionization mode, yes. And here he puts this compound, he calls this whatever he called it. This is the parent mass overcharge that he knows about, and this is the daughter. This is the pair he was talking about. And the 12 time is it's the amount of time it takes within the ionization chamber. And the cone here is the voltage of the cone, and the collision energy is the energy voltage, or not voltage, the energy that the parent is experiencing. So you can play with these knobs and dials until you get the highest intensity, which is usually done in tuning phase. And this guy is just trying to optimize the collision energy. So it's very interesting, very powerful wood, very powerful instrument. So how does it work? Is it magic? No, it's all science, but material will be provided as an extracurricular material. But if you really want to find out how these things work, how the nitty-gritty details of how a biology lab instrument work and their mathematics behind it, you can join our club next semester, next summer, I mean. We will talk all about it. We will see how these things work, and here's a sneak peek into what you might find there. Um, this is a potential field that is created from the quadrupole. Here, like you can imagine an ion here, it's a positive ion. It tries to go to the negative, then gets pushed back, then tries to the negative, then gets pushed back. And it's like this saddle here. This is the equation for the potential field, of course. We will derive it and we will know how it's all brought up. We will read all the books that necessary for it. But basically, this is your ion. It tries to fall down, but it cannot. It just keeps jiggling around. So this is the RF mode, the where the quadrupole acts as an ion duct. It can't escape. Okay, so mass spectrometry is very powerful for proteomics, and we will be talking about this in the next semester or next chapter, hopefully. There are a lot of things you can talk about. There is a lot of things you can do with the data that comes out from a mass spectrometer. Yeah, look at this. Also, remember when I said about when I talked about the chromatography and their conjugation with mass spectrometry? This is basically it. Look, from time 0 to time 10, here are the column separation, the separation of the sample using columns. You can separate it using polarity, using hydrophobicity, using whatever you want to use. This is the way you do it, or using cation exchange or ion exchange method. So this one it gets separated, then goes through the mass spectrometer, where the mass spectrometer does a scanning mode on it. Look at that, it only lets the smaller mass and then the highest mass. So look at this peak. There's something here, right? Then the smallest and most, oh, there's another peak over here. It has to be something important. Then you go through this, and oh, also, where does this peak come from? Okay, this huge peak is actually all of these peaks added together. It's called the TIC, total ion count. These are all ion counts, okay, for each mass overcharge, and it just gives each of these are like frames. It like adds frame after frame after frame after frame until it gives you all of this huge peak right here. That's why we said in the first slide that we look at the mass spectrometer as a detector, because look at this whole thing is just the addition of all these small uh, uh, fragmentation pattern or mass spectrum. So it's a very powerful tool. There's a lot of things you can do with it. The amount of data that you come up with it from it, it's very powerful. You can use it for a lot of things. You can find molecular markers or metabolic markers or whatever in cancer patient or in Alzheimer patient. You can do a lot of statistical analysis on it. You can do an ROC AUC for how well this marker that you picked is good for your detection. You can do a PCA analysis to differentiate each um, to separate each component here for their um, like what do we call it here? You separate each of them based on how well they define your data or define your your group that you're studying, like Alzheimer group or cancer group and so on. And this guy here, it said a heat map of different tissues here that he had different like proteins and their concentration. You can measure the concentration using this one. Um, this is a value of important value score or the Shapley value. This tells you how important each of these components from your mass spectrum contributed to the proper classification of a disease. These are all can be brought up from a mass spectrometer, and it's a very powerful tool. So next time we will talk about it in biostatistics or in the proteomics course. These are the textbooks that I used, and thank you. And sorry if I took a bit of too much of your time, but it's a very powerful um, instrument that it needs time to be talked about. So thank you.